95% of the universe is missing from our picture. All the stars, planets, and galaxies we see are just a tiny fraction of what is actually out there, floating in a vast cosmic sea of darkness we cannot see or explain. This is the central puzzle of modern cosmology, the biggest unsolved mystery in all of science. We call these unknown components dark matter and dark energy. Our best theory of particles and forces, the Standard Model, has no place for them. They are ghosts in the cosmic machine, invisible forces shaping everything, and their existence means our fundamental picture of reality might be profoundly incomplete. By the end of this exploration, you will understand a radical idea that could solve this entire crisis: the possibility that our universe has hidden extra dimensions of space. This is not science fiction, but a serious scientific framework that could completely reshape our search for the dark universe, turning the hunt for unknown particles into a map of reality's true geometry. What if the answers we seek are not just hidden in the darkness, but in the very shape of space itself? Our best map of reality, the Standard Model of particle physics, is a triumph of human ingenuity. It describes the fundamental building blocks of matter and the forces that govern them with breathtaking precision. Yet for all its power, this magnificent theory is staring at the cosmos with a profound sense of confusion. Its greatest failure is not a minor miscalculation, but a complete inability to account for the universe we actually observe. The cosmos presents two monumental puzzles that the Standard Model simply cannot solve. The first is dark matter. We know it is there because of its gravitational pull. Look at a spinning galaxy, and you will see its outer stars whipping around far too fast. According to the visible mass of stars and gas, those stars should be flung out into the void. Something invisible with immense gravity is holding that galaxy together. This same unseen mass bends the light from distant galaxies, creating cosmic mirages we call gravitational lensing. The evidence is overwhelming: a shadowy substance that does not emit, absorb, or reflect light, yet outweighs all normal matter by a factor of 5 to 1. The Standard Model has no particle that fits this description. Every known particle, from quarks to neutrinos, has been ruled out. Dark matter demands something entirely new, a particle that simply does not exist in our current catalogue of reality. The second, even more baffling puzzle is dark energy. In the late 1990s, astronomers made a shocking discovery. The expansion of the universe is not slowing down, as everyone expected from the pull of gravity. It is speeding up. Some repulsive force woven into the fabric of space itself is pushing galaxies apart at an ever-increasing rate. We label this force dark energy, and in our equations, it appears as a number called the cosmological constant. Here lies the problem. When physicists try to calculate what this number should be based on quantum theory, they get an answer that is wrong by a factor of 1 followed by 120 zeros. It is arguably the worst theoretical prediction in the history of science. This is not a small gap. It is a chasm of misunderstanding so vast it screams that we are missing something fundamental. Together, dark matter and dark energy represent not just holes in our knowledge, but a direct confrontation. Our most successful theory of the very small is completely silent on the nature of 95% of the universe. This is the crisis that forces a paradigm shift. When the map no longer matches the territory, you must consider the possibility that you have been reading the map wrong all along. This crisis demands we reconsider the very stage upon which reality plays out. We are accustomed to living in a world of 3 spatial dimensions: length, width, and height. But what if space itself has more properties than we can directly perceive? The idea of hidden dimensions is not a modern invention. In the early 20th century, physicists Theodore Kaluza and Klein proposed a radical solution to a different problem: the unification of gravity and electromagnetism. Their elegant idea was to add a single, unseen extra dimension to the equations of Einstein's general relativity. In their framework, the force of electromagnetism was not a separate entity, but simply a manifestation of gravity operating in that hidden fifth dimension. From our three-dimensional perspective, we would only see a shadow of the full geometry, interpreting it as two distinct forces. While this specific unification did not pan out, the core concept was revolutionary. It suggested that the fundamental forces we experience could be the direct result of the shape and structure of higher dimensional space. To visualize how this could work, picture a long, thin garden hose stretching across a field. From a great distance, it looks like a simple one-dimensional line, but an ant crawling on its surface knows the truth. The hose has a second dimension, its circular circumference curled up into a tiny loop. The ant can move along the length of the hose, our familiar large dimension, but it can also travel in a tiny circle around the hose itself, a dimension so small it is invisible from far away. Our universe could be structured in a similar way. Beyond the three expansive dimensions we navigate daily, there could be additional spatial dimensions curled up or compactified at an unimaginably tiny scale, perhaps 1 billion times smaller than an atom. We are like two-dimensional creatures living on the surface of that hose, completely unaware of the circular dimension because it is folded up beyond our perception. Every point in our three-dimensional space could secretly harbor this complex miniature geometry. This is the profound legacy of Kaluza and Klein, a shift in thinking that transforms physics from a search for particles to a study of geometry. The properties of particles themselves, their mass and charge, might not be intrinsic qualities but notes played on the tiny, hidden strings of a multidimensional universe. The elegant geometry of hidden dimensions found a powerful new home in the late 20th century with a theory that attempts the ultimate unification, string theory. This framework is not a choice but a mandate for extra dimensions, a mathematical requirement for its very existence. String theory proposes that the fundamental constituents of the universe are not point-like particles, but unimaginably tiny, vibrating loops of energy, strings. The different vibrational patterns of these strings correspond to different particles, much like different vibrations of a violin string produce different musical notes. A single string vibrating one way might be an electron, vibrating another way could be a photon, a particle of light. It is a beautifully simple idea, but it comes with a profound consequence. For the mathematics of these vibrating strings to be consistent, for the theory to include gravity and avoid nonsensical infinities, the equations only work if the universe has more than the three spatial dimensions we experience. Specifically, most versions of string theory require 10 or 11 total dimensions of spacetime. Think of it like this: a guitar string can vibrate in many complex, beautiful ways, but only if it is stretched across a guitar. The instrument's shape, its dimensions, determine what music is possible. In the same way, the vibrational notes of fundamental strings, which become the particles and forces we see, are only possible if the stage they play on, spacetime itself, has this specific higher dimensional geometry. So where are these extra dimensions? Why don't we see them? The leading idea is compactification. Imagine one of those extra dimensions is a circle, but a circle so incredibly tiny it is curled up at a scale known as the Planck length, about 1 billion trillion times smaller than the nucleus of an atom. At every single point in our familiar three-dimensional space, this tiny, circular dimension exists, but it is far too small for any instrument, any particle, any form of energy we currently possess to probe or move through in a meaningful way. We are confined to the three large, expansive dimensions, like ants living on the vast surface of a leaf, completely unaware of the leaf's microscopic thickness. The critical insight is that the specific way these extra dimensions are curled up and shaped, their topology and geometry, is not arbitrary. It acts like the internal wiring of the cosmos. The exact shape determines the possible vibrational patterns of the strings, which in turn fixes the constants of nature, the masses of particles, the strength of forces, even the number of particle families we observe. In string theory, the answer to the question, why is an electron so light and a proton so much heavier, might not be found by discovering a smaller particle inside them, but by understanding the specific, hidden geometry of a dimension we cannot see. This transforms our search for fundamental laws from a particle hunt into a cosmic cartography project. We are trying to map the invisible, folded geometry of reality itself, a geometry whose shadows might finally explain the darkness we see all around us. This radical shift in perspective leads to an even more startling possibility, one that could solve a mystery we have lived with since Newton. Gravity is bafflingly weak. Think about it for a moment. The entire mass of the Earth, all 6 sextillion tons of rock and metal, pulls on you with a force you can overcome with a simple hop. Yet a tiny fridge magnet, using the electromagnetic force, can defy that entire planetary pull and stick to the metal door. Gravity is weaker than the other fundamental forces by a factor of a trillion. Why string theory and the geometry of hidden dimensions offer a profound and elegant answer. Gravity might be weak because it is not entirely here. It could be leaking away. To understand this, we need a new picture of our universe, often called the braneworld scenario. Imagine our entire three-dimensional cosmos, all the galaxies, stars, and planets, is not floating freely in higher dimensions, but is instead a three-dimensional membrane, or brane for short. This brane is like an immense, impossibly thin sheet of reality, suspended within a larger, higher-dimensional space called the bulk. In this picture, the particles that make up you, me, and everything we see, the quarks and electrons of the standard model, are not free to leave. They are like ink droplets trapped on the surface of that sheet, forever stuck to our brain. Their vibrations are confined to our slice of reality, but gravity is different. In Einstein's theory, gravity is not a force in the traditional sense, but the curvature of spacetime itself. If our brain is embedded in a higher dimensional bulk, then the fabric of spacetime it is made from can extend into that bulk. Gravity, as the geometry of that fabric, would not be confined. It could seep off our brain and spread out into the extra dimensions. This is the key conceptual leap. While light and matter are painted onto the canvas of our brain, gravity is a ripple in the canvas itself, and that ripple can travel into the unseen depths around us. Now picture a source of gravity on our brain like a star. Its gravitational influence spreads out like the light from a bulb. In a purely three-dimensional world, that light spreads over the surface of an ever-expanding sphere, growing dimmer with distance. But if gravity can leak into an extra, compact dimension, it spreads over the surface of a higher dimensional shape. Just as a whisper in a small room is loud but becomes faint in a vast cathedral, the strength of gravity is diluted as it spreads into this larger, hidden volume. By the time we feel its pull here on the brain, it is only a faint shadow of its full intensity. The force that shapes galaxies and holds planets in orbit is not feeble at its source. It is simply spread thin across realities we cannot perceive. This leakage offers a breathtakingly simple explanation for gravity's apparent weakness, not as a fundamental property, but as a geometric accident of our confined perspective. It suggests that when we measure the tug of a planet, we are not sensing the whole story, only the part that remains trapped in our world. This geometric leakage of gravity provides the first crucial clue, a crack in the door through which we can glimpse a radical new identity for dark matter. If gravity can seep into the bulk, what else might be out there? Perhaps dark matter is not a missing particle in our universe, but something from outside it entirely. One compelling idea within the braneworld scenario is that dark matter could simply be ordinary matter living on a parallel brane. Picture our three-dimensional universe as one sheet of paper in a vast cosmic stack. Another sheet, another entire universe with its own stars and planets, could be floating incredibly close to ours in a higher dimension, separated by a gap far smaller than an atom. The particles of that other brane are completely invisible to us because light and the forces that bind atoms are stuck to their own sheet. They cannot cross the gap. But gravity, the geometry of the bulk, can. The gravity from stars and planets on that neighboring brane would leak into the bulk and wash over our brane, pulling on our galaxies. From our perspective, we would feel the unmistakable gravitational tug of immense amounts of mass, but we would see absolutely nothing. It would appear to us exactly as dark matter does, a ghostly gravitational presence with no visible source. In this view, the dark matter halos enveloping galaxies might be the faint gravitational shadows of entire parallel worlds, hovering just beyond the reach of our light. Alternatively, the answer might be woven into the fabric of the extra dimensions themselves. Remember, these curled-up dimensions are not static. They can vibrate and oscillate, much like the surface of a drum. In string theory, these vibrations are called Moduli fields. Each specific pattern of vibration corresponds to a different property of our observed universe. Some of these vibrational modes, however, could manifest in our three-dimensional world as elusive, massive particles that interact with virtually nothing except gravity. They would be born from the geometry of space, not from any particle collision on our brane. These Moduli particles would flow through our world like ghosts, barely noticing the matter we are made of, yet collectively their mass would generate the gravitational pull we attribute to dark matter. Here, dark matter is not foreign matter from another brane, but a direct echo, a deep bass note from the vibrating hidden geometry of our own reality. There is another, more dramatic possibility born from a higher dimensional early universe. In the intense heat and density of the Big Bang, when all dimensions were likely unfurled and dynamic, the physics of the bulk could have allowed for the formation of primordial black holes on scales impossible in our three-dimensional world. These would not be the black holes formed from collapsing stars, but knots of spacetime curvature born in the first moments of everything. If they formed before the extra dimensions compactified, their properties would be dictated by higher dimensional gravity, making them potentially far more numerous and of different masses than we expect. Such objects wandering the cosmos today would be virtually invisible yet possess tremendous gravity. They could collectively account for the dark matter holding galaxies together. Each one would be a fossil, a relic of a time when all of reality's dimensions were laid bare, a permanent reminder of the universe's true, larger shape. Each of these ideas transforms dark matter from a missing puzzle piece into a cosmic signpost. It is no longer merely a substance we have failed to find, but potentially a message, a gravitational signature pointing to the architecture of everything. The hunt for dark matter becomes a forensic investigation of spacetime's hidden geometry, searching for the fingerprints of other branes, the whispers of vibrating dimensions, or the ancient scars of a higher dimensional birth. If dark matter is a gravitational whisper from hidden geometry, then the particle of gravity itself holds the secret. In our quest to quantize the forces of nature, physicists have long predicted the existence of the graviton, the hypothetical messenger particle for gravity, analogous to the photon for light. According to quantum theory, every force is transmitted by such particles. Yet the graviton has never been detected, and for good reason. In our standard four-dimensional spacetime, its interactions are so incredibly feeble that spotting one is practically impossible. But in a universe with large extra dimensions, this story changes dramatically, and the graviton's behavior could solve two mysteries at once. In theories where the extra dimensions are not curled up at the Planck scale, but are relatively large, perhaps as big as a fraction of a millimeter, the rules of the game are rewritten. The dilution of gravity we experience is not because the extra dimensions are tiny, but because gravity is spreading into a larger volume that is still, on a cosmic scale, compact. In such a scenario, the fundamental scale of gravity could be much, much lower than we think, not at the unreachable Planck energy, but at energies within the reach of our most powerful machines. This leads to a staggering possibility at places like the Large Hadron Collider. When protons are smashed together at nearly the speed of light, they release a tremendous amount of energy, which condenses into new particles. In a world with large extra dimensions, some of that energy could produce real gravitons, and here is the critical twist. These newly minted gravitons, as carriers of gravity, would not be confined to our brain. They would immediately travel or propagate off into the bulk, the higher dimensional space. From the perspective of our detectors, it would look as if a significant amount of energy from the collision simply vanished without a trace. The event would be marked by an imbalance, a signature of missing momentum. This is not a flaw in the experiment, it is a potential fingerprint of a graviton escaping our dimensional plane. Remarkably, this exact signature is what many dedicated dark matter searchers are looking for. When scientists at the LHC hunt for dark matter, they often design their searches around events where known particles are produced in one direction, but something invisible recoils in the opposite direction, carrying away energy and momentum. In the standard dark matter particle hypothesis, that invisible something is a weakly interacting massive particle, or WIMP. But in the extra-dimensional picture, that invisible something could be a graviton sailing off into the bulk. The experimental signal is identical, missing transverse momentum. This creates a profound and direct link. The hunt for dark matter at particle colliders is not just a search for a new particle, it is a test of the dimensionality of spacetime itself. Every collision is a miniature probe of the universe's architecture, a flash of energy that might briefly illuminate the pathways into higher dimensions. If we were to see an excess of these missing momentum events at certain energies, it might not point to a dark matter particle sitting in our catalogue, but to the moment a piece of our reality, a graviton, stepped out of our world and into the broader, hidden geometry of everything. The culprit for the missing energy would not be a hidden particle, but a hidden dimension. The search for dark matter has long been a story of deep silence and profound patience. For decades, the leading hope has been a hypothetical particle known as a WIMP, a weakly interacting massive particle. The logic was beautifully simple. If dark matter is a relic from the hot, dense early universe, and if it interacts with ordinary matter through the weak nuclear force just enough to stay in thermal equilibrium, then its predicted abundance and mass would align almost perfectly with what we observe. This elegant coincidence, known as the WIMP miracle, drove an entire generation of experiments. These are feats of engineering and isolation, like the LUX Zeppelin detector, buried a mile underground in a former gold mine, or Xeno NNT submerged in a mountain in Italy. Their goal is to catch the uncatchable, to witness the impossibly rare moment a WIMP from the galactic halo bumps into the nucleus of a xenon or argon atom deep within a vat of ultra-pure liquid. These labs are shielded by rock and water, encased in layers of copper and lead, all to block out the constant rain of cosmic rays and natural radioactivity, creating the quietest places on Earth to listen for a single, ghostly ping. But after years of listening, the silence has grown deafening. No definitive signal has been found. The parameter space where WIMP were expected to live has been shrinking, squeezed by the relentless sensitivity of these detectors. This growing quiet is not necessarily a failure, but a powerful clue. It is telling us that dark matter might be something even more alien than we imagined, something that does not play by the rules of our familiar forces. This is where the geometry of hidden dimensions reshapes the entire detective story. If dark matter is not a particle on our brain, but an entity of the bulk, its interaction with our world could be fundamentally different. The coupling might not be through the weak force at all, but through gravity and gravity alone. For a direct detection experiment designed to sense a nuclear recoil, this is a paradigm shift. The energy transferred in a gravitational interaction is astronomically smaller than that from a weak force collision. A WIMP detector waiting for a bump would be like a microphone listening for a symphony, only to have the music arrive as a faint change in air pressure 1,000 miles away. It would never register. The search must evolve from listening for a knock on the door to sensing the subtlest bend in the floorboards. This demands entirely new kinds of sensors. Researchers are now pioneering quantum devices of incredible sensitivity, things like supercooled nanomechanical resonators or clouds of ultra-cold atoms. The idea is to monitor not for a sudden impact, but for a continuous, gentle tidal force. If a clump of bulk-based dark matter, perhaps a primordial black hole or a soliton of Moduli fields, were to pass through our solar system, its gravity would minutely stretch and compress space itself as it moves. These next-generation detectors aim to measure that infinitesimal distortion, the whisper of spacetime curvature moving through the lab. Another exotic signature arises from the dynamics of the extra dimensions themselves. If they are not static but can vibrate or undergo sudden topological shifts, these events could send ripples through the bulk that manifest in our brain as bursts of very low-frequency gravitational waves. Our current observatories like LIGO are tuned to the high-frequency crashes of black holes and neutron stars, but a transient event in the geometry of a hidden dimension might produce a gravitational wave with a frequency so low it takes years to oscillate, a slow, cosmic sigh moving through the fabric of everything. Detecting this would require a completely different approach, like monitoring the precise timing of signals from an array of pulsars across the galaxy, using them as a galaxy-sized gravitational wave antenna. The quiet in the deep underground labs is not an end but a beginning. It is pushing us to broaden our definition of a signal, to consider that the dark universe might not announce itself with a particle collision we can see, but with a gentle, geometric nudge we must learn to feel. The next generation of experiments will not just look for what is missing, but will listen for the new physics in the shape of the silence itself. The profound silence in our detectors points toward a geometric answer for dark matter, but the universe presents an even more pressing enigma. While dark matter sculpts the cosmos on grand scales, something else is governing its ultimate fate, a force not of structure but of dissolution. This is dark energy, the mysterious agent causing the expansion of the universe to accelerate. For decades, the leading explanation has been the cosmological constant, an unchanging energy density woven into the vacuum of space itself. But that explanation comes with an unbearable price, a theoretical prediction so catastrophically wrong it hints we are misreading the equation entirely. What if dark energy is not a constant at all, but a symptom, a side effect of the hidden dimension's slowly changing shape over billions of years? Imagine those extra curled-up dimensions not as static, immutable loops, but as dynamic, living geometry. They have a size, a shape, a tension. In the fiery first moments after the Big Bang, they were likely dynamic and unstable, but as the universe cooled, they settled into a specific, stable configuration. This is the compactification that defines our physics, but what if that stability is only temporary on a cosmic timescale? What if, over the eons, these dimensions are very gradually relaxing, unwinding, or shifting toward a new, more stable form? This slow evolution would not be a violent event, but a glacial transformation of reality's underlying architecture. From our perspective, trapped on our three-dimensional brain, we would not see the dimensions themselves change. We cannot perceive them directly. Instead, we would feel the consequences in the only way we can, through the geometry of the space we inhabit. As the hidden dimensions evolve, the effective laws of physics in our visible universe would subtly shift. The vacuum of space, which we think of as empty, is in this framework intimately connected to the full, higher dimensional geometry. A change in that geometry changes the energy content of our vacuum. If the compact dimensions are slowly expanding, even by an infinitesimal amount over billions of years, the energy required to maintain that new configuration would seep into our three-dimensional world. This infusion of energy would act like a constant, gentle pressure on the fabric of our spacetime, pushing galaxies apart. Crucially, this pressure would not be a true cosmological constant, a fixed number etched into the universe's foundation. It would be a dynamic phenomenon, a side effect of a slow-motion geometric transition happening in the realms we cannot see. The accelerating expansion we measure would be an illusion of perspective, a three-dimensional shadow of a multidimensional metamorphosis. To visualize this, think of the surface of a slowly inflating balloon. An ant living on that surface would see every other ant moving away, and would conclude that some repulsive force is embedded in the two-dimensional rubber of its world. But the real cause is not on the surface, it is in the third dimension, the act of inflating the balloon itself. In our universe, the accelerating separation of galaxies might be the surface-level symptom of a higher dimensional breath, the gradual unwinding of compactified space. This geometric view offers a potential escape from the cosmological constant problem. The infamous mismatch of 120 orders of magnitude arises from calculating the energy of our vacuum assuming three static dimensions of space. If the vacuum energy is not a fundamental property but an emergent one, dictated by the evolving shape of extra dimensions, then that calculation starts from a flawed premise. The number we measure would not be a fundamental constant to be predicted, but a snapshot of a process, a readout of the cosmic geometry at this particular moment in the universe's long life. It transforms dark energy from a mysterious substance to a cosmic clock, ticking to the rhythm of hidden dimensions slowly finding their final form. The fate of the universe, then, may not be written in a simple constant, but in the silent, patient geometry of the unseen. This staggering mismatch is not a minor error. It is a scream from the mathematics that our entire framework is incomplete. Quantum field theory, our description of particles and forces as fields flickering in and out of existence in empty space, suggests that the vacuum itself should be seething with a colossal intrinsic energy. Every cubic centimeter of so-called empty space, according to these calculations, should contain more energy than all the matter in the observable universe combined. This energy would exert a gravitational repulsion so strong that the universe would have blown itself apart instantly after the Big Bang. Yet when we look out with our telescopes, we measure a universe that expanded gently for billions of years before a very slight acceleration began. The observed dark energy is there, but it is 120 orders of magnitude weaker than the simplest quantum prediction. This is the cosmological constant problem, the most severe disconnect between theory and observation in all of science. It implies we are either profoundly misunderstanding the vacuum, or we are missing a cancellation mechanism of unimaginable precision. This is where the geometry of hidden dimensions offers not just an alternative, but a potential escape route. The key idea is dilution. Remember, in the braneworld picture, our observable universe is a three-dimensional sheet embedded in a higher dimensional bulk. The vacuum energy we calculate in our theories is the energy density on our brane, the energy per unit volume in our three familiar dimensions. But gravity, which feels the effect of this energy, does not only operate in our three dimensions. It spreads out or dilutes into the full volume of the higher dimensional space. To grasp this, think of a single drop of incredibly potent ink. If you place that drop in a small thimble, the water becomes deeply and darkly colored. But if you take that exact same drop and let it diffuse into an entire swimming pool, the color becomes so faint it is almost invisible. The ink has not vanished, its total amount is the same, but its concentration, its density in any given liter of water, has been dramatically reduced. Now apply this to the vacuum energy. The quantum calculation gives us the equivalent of that potent drop, an immense energy density confined to our three-dimensional brane. But if that energy is allowed to spread or gravitate into the larger volume of the extra dimensions, its effective density from the perspective of our three-dimensional world plummets. The repulsive gravitational effect we would feel is not based on the raw, concentrated energy on the brane, but on its diluted value after spreading through the bulk. The vast hidden volume acts as a cosmic buffer, absorbing the fierce intensity of the quantum vacuum and leaving behind only the faint, residual pressure we measure as dark energy. This geometric dilution transforms the problem. Instead of requiring a miraculous, fine-tuned cancellation between unrelated numbers to get the tiny value we see, the smallness of dark energy could be a natural consequence of the size of the extra dimensions. The larger the volume of the hidden dimensions, the more the vacuum energy is diluted and the weaker the resulting acceleration. In this light, the cosmological constant is not a fundamental number we must predict, but an emergent one we measure, a readout of the hidden geometry's scale. The fact that we see any acceleration at all could be a clue, a whisper telling us that the extra dimensions, while compact, are not infinitely small, but have a size that leaves just this faint gravitational imprint on our expanding universe. But if dark energy is a dynamic echo of evolving geometry, could the very origin of our universe be a similar kind of geometric event? This line of questioning leads to some of the most dramatic models born from the braneworld idea, frameworks that completely rewrite the story of the Big Bang itself. In these models, the moment of creation is not a singular explosion from an infinitely dense point, but a collision, a meeting of worlds in the higher dimensional bulk. Two of the most compelling of these are the Ekpyrotic and cyclic models. The name Ekpyrotic comes from the ancient Greek word for conflagration or great fire, but here the fire is one of kinetic energy transforming into the heat of a new beginning. Picture two immense parallel branes, each a complete three-dimensional universe, floating in a higher dimensional space. They are not static but moving, drawn together by a force across the bulk. In the Ekpyrotic scenario, our universe begins not with a bang but with a gentle touch. These two branes slowly approach each other and collide. The kinetic energy of that collision, spread across the entire surface of our brane, is converted into an immense burst of heat and particles. From our perspective, trapped on one of those branes, it would appear exactly as a hot, dense, expanding Big Bang. All the matter and radiation that fills our cosmos is not born from a singularity, but from the energy of a cosmic impact in a higher dimension. This reframing has profound implications. It naturally explains why our universe appears so uniform on large scales, a long-standing puzzle called the horizon problem. In the standard Big Bang model, regions of space now on opposite sides of the observable universe were never in causal contact, yet they have the same temperature and properties. How did they coordinate? In the Ekpyrotic model, the collision and heating happen simultaneously across the entire pre-existing brane, providing a built-in mechanism for that uniformity. But what happens after the collision? This is where the cyclic model expands the story into a potentially endless cosmic rhythm. After the branes collide and rebound, they fly apart, stretched and emptied by the resulting expansion, which we experience as dark energy driving the universe apart. But the attractive force between them remains. Eventually, the expansion slows, halts, and reverses. The branes are drawn together again across the vast, dark bulk, culminating in another collision and another fiery rebirth. In this breathtaking vision, the Big Bang is not the beginning of time, but the latest chapter in an eternal cycle of creation, dissolution, and recreation. Our entire cosmic history, from the first particles to the last fading galaxies, is but one phase in an oscillation that has no start and no end. Within this grand cyclical picture, dark energy finds a new and dynamic identity. It is no longer a mysterious constant or a symptom of unwinding dimensions, but a direct consequence of the brane's own inherent tension and its interaction with the bulk. The force that is currently pushing our universe apart could be the very same force that, in the far future, will be overcome by the attraction to the other brane, setting the stage for the next collision. This transforms dark energy from a puzzling endpoint into an essential plot device in an ongoing cosmic epic, the engine that drives the cycle forward. These models are not just philosophical speculation, they are mathematically rigorous frameworks that make testable predictions. For instance, they predict a very specific pattern, or lack thereof, in the primordial gravitational waves left over from the brane collision, distinct from the pattern predicted by inflationary Big Bang models. Future observatories like space-based gravitational wave detectors could one day find a signature in the cosmos's oldest light that points not to a rapid inflation, but to a slow, deliberate collision of worlds. This is the power of the geometric viewpoint. It takes our greatest mysteries, the origin and fate of everything, and recasts them as chapters in a higher dimensional story, a story written not in particles, but in the moving, colliding, and evolving geometry of reality itself. The quiet evolution of hidden geometry could even repopulate our universe with ghostly echoes of familiar matter. One of the most concrete predictions from the original Kaluza-Klein framework is the existence of what physicists call a Kaluza-Klein tower. This is not a physical structure but a spectrum of particles, a direct and testable consequence of living in a universe with compactified extra dimensions. To understand this, let us return to the analogy of the garden hose. An ant on that hose can move in two ways along its long length and in a tiny circle around its circumference. Now imagine the ant is not just walking but vibrating with energy. It can vibrate along the long direction which corresponds to a low energy state, our familiar world. But it can also vibrate around the tiny circular dimension. Because that circle is so small, vibrating around it requires a very specific, much higher amount of energy. It is like plucking a guitar string. The shorter the string, the higher the pitch. In our universe, every fundamental particle, every electron and quark is like that ant. It exists in our three large dimensions, but it also inhabits those tiny, curled-up extra dimensions. A particle can therefore have different vibrational states in those hidden directions. The lowest energy state, where it is not vibrating in the extra dimensions at all, is the ordinary particle we know and detect. But the mathematics of compact spaces dictates that higher energy vibrational modes are not only possible, they are required. These are the excited states, the higher notes on the string of reality. Each one would appear in our three-dimensional world as a new particle, with the same electric charge and other quantum properties as its ordinary counterpart, but with a vastly greater mass. For every electron we know, there could be a tower of heavier electron-like particles, each one a rung on a ladder stretching upward in mass and energy. The first excited state might be a particle that looks just like an electron but weighs 1,000 times more. the next rung could be 10,000 times heavier, and so on. This tower is the Kaluza-Klein tower, a direct fingerprint of the compact dimension's size and shape. The spacing between the rungs tells us the radius of the hidden circle. The pattern of masses reveals its geometry. Now consider the lightest particle in such a tower. It would be stable because there is no lighter state for it to decay into that carries the same conserved charges. If the lightest Kaluza-Klein particle is electrically neutral and interacts only very weakly, it would be a perfect candidate for dark matter. It would have been produced in the hot early universe, frozen out as relics, and now drift through galaxies, invisible yet massive, their gravity shaping the cosmos. In this scenario, dark matter would not be one new exotic particle, but an entire population of geometric echoes, the lightest members of towers that shadow every particle we know. The search for it transforms completely. Instead of looking for one missing particle, we might be looking for a pattern, a harmonic series of masses emerging in the debris of particle collisions. At a machine like the Large Hadron Collider, if physicists were to see not just one new particle, but a series of them with identical properties except for their mass, appearing at precise energy intervals, it would be a smoking gun. It would be direct, undeniable evidence for extra dimensions. The discovery would be twofold, solving the identity of dark matter by identifying the lightest of these tower particles and simultaneously mapping the hidden geometry that generates them. The particle zoo would not be a random collection of discoveries, but a musical scale played on the strings of a higher dimensional universe, each new note revealing a little more of the shape of everything. The search for a geometric explanation leads us directly to one of the most persistent puzzles in all of physics. We call it the hierarchy problem, and it is a question of scale that feels almost personal. Why is the universe built with such wildly different strengths? The weak and strong nuclear forces operate at a scale quintillions of times more powerful than gravity. This is not a minor difference, it is a chasm that makes the existence of complex structures, from atoms to planets, seem like a miraculous accident. If gravity were just slightly stronger relative to the other forces, stars would burn out in a flash and planets could never form. The fact that we are here to ponder this question suggests something is protecting this delicate balance, or perhaps hiding gravity's true nature. The hierarchy problem is the formal expression of our earlier observation that gravity is unbelievably feeble, and it is the engine that drives much of the search for physics beyond the standard model. For decades, the leading solution involved a concept called supersymmetry, which proposes a shadow partner for every known particle. But like the search for WIMP, evidence for supersymmetry has remained elusive. This persistent silence opened the door for a far more radical geometric answer, one that redefines the very meaning of fundamental scale. In the late 1990s, physicists Nima Arkani-Hamed, Savas Dimopoulos, and Georgi Div-Oli proposed a model, now known as the AD model, that turned the hierarchy problem on its head. Their breathtaking idea was this: gravity is not inherently weak. It only appears weak to us because we are trapped on a three-dimensional brane, while gravity is free to spread out into large extra dimensions. Imagine our three-dimensional universe is a vast, flat sheet of paper. In the traditional view, with tiny, curled-up dimensions, gravity is like a whisper confined to that sheet. But in the AD proposal, the extra dimensions are not microscopic. They could be as large as a fraction of a millimeter, a scale just beyond the reach of our current tabletop experiments. Our entire universe, with all its galaxies and stars, is confined to this sheet, but gravity, as the curvature of spacetime, is not stuck to it. It can leak off into this surprisingly roomy higher dimensional volume. Now picture a star on our Brane. Its gravitational field spreads out like light from a bulb. In our three-dimensional world, that light dims quickly as it spreads over the surface of an expanding sphere. But if gravity can seep into even one extra dimension of this new, larger size, it spreads over the surface of a four-dimensional sphere. The same amount of gravitational influence is diluted across a vastly greater geometric volume. By the time we feel its pull here on the Brane, it is only a faint remnant. The incredible weakness of gravity is not a fundamental property, but a simple accident of our perspective, a cosmic illusion created by the geometry of hidden space. This elegantly solves the hierarchy problem by eliminating it. There is no fundamental imbalance between gravity and the other forces, because the true, fundamental scale of gravity is not the incredibly high Planck energy we calculate in 3 dimensions. It is a much lower, more reasonable energy comparable to the scale of the other forces. The immense gap we measure is just an artifact, a mirage created by gravity's escape into the bulk. This model makes a stunning and testable prediction. If there are extra dimensions as large as 1/10 of a millimeter, then Newton's famous law of gravity, which states that the force weakens with the square of the distance, should break down at exactly that scale. At distances smaller than the size of the extra dimension, gravity would begin to feel the full effect of the higher dimensional geometry, and its strength would fade not with the square, but with the cube or the fourth power of the distance. This means that if we could measure the gravitational attraction between two objects placed incredibly close together, thinner than a human hair, we might see a deviation from the law that has governed our understanding for over 3 centuries. This prediction has launched a new frontier in experimental physics, the search for deviations from Newtonian gravity at sub-millimeter scales. Experiments use exquisitely sensitive torsion balances, micro-fabricated cantilevers, or even levitating superconductors to measure the gravitational force between minuscule test masses separated by gaps smaller than the width of a dust mote. These are not grand astronomical observatories, but quiet, precise machines on laboratory benches, hunting for a whisper of curvature in the fabric of space at a human scale. A detection in one of these experiments would be a direct, earthbound signal of the universe's true multidimensional architecture. It would prove that the hierarchy problem is solved by geometry, and in doing so, it would forge an intimate link between the deepest puzzles of particle physics and the nature of gravity itself. The hunt for dark matter and the quest to understand gravity's weakness would converge on a single, profound truth, written in the hidden dimensions of our world. The quiet hum of a laboratory bench could hold the key to the universe's true shape. While telescopes scan the vast cosmos, an equally profound search is happening at the opposite extreme, in the realm of the vanishingly small. Here, physicists are not looking out, but looking in, probing the fabric of space itself at distances thinner than a human hair. Their goal is to catch gravity in the act of behaving strangely, to witness the moment Newton's ancient law breaks down and reveals the whisper of a hidden dimension. This is the frontier of tabletop cosmology, where the grand mysteries of dark matter and dark energy are pursued with exquisitely sensitive miniature machines. The most direct approach uses devices called torsion balances. Imagine a tiny horizontal bar suspended by an incredibly thin fiber, often made of fused silica, thinner than a spider's silk. At each end of this bar hangs a minuscule test mass, a gold sphere or a small disk. Just millimeters away, a larger, oscillating attractor mass is carefully moved closer. The gravitational pull from this attractor should cause the tiny bar to twist on its fiber, a twist measured by reflecting a laser beam off a mirror attached to the bar. The entire apparatus is sealed in a vacuum chamber to eliminate air currents, shielded from magnetic fields, and isolated from vibrations. Scientists then measure the gravitational force between the masses as the gap between them is reduced to distances smaller than the width of a sheet of paper. They are searching for a precise deviation. At scales above a few tenths of a millimeter, gravity should follow Newton's inverse square law perfectly. But if an extra dimension exists at that scale, gravity would begin to seep into it. Its force would weaken not with the square of the distance, but with the cube or a higher power. The twist of the fiber would be just a fraction different than predicted. Detecting that fractional difference is like trying to hear a pin drop in a quiet room from a mile away, requiring a silence and precision that pushes the limits of engineering. Another powerful probe arises from a curious quantum phenomenon, the Casimir effect. In the pure vacuum of space, quantum theory tells us that virtual particles constantly flicker in and out of existence. When two perfectly smooth, neutral metal plates are brought extremely close together, fewer types of these virtual fluctuations can fit between them than outside them. This creates a subtle pressure difference, an attractive force that pulls the plates together. This Casimir force is exquisitely sensitive to the geometry of empty space. If extra dimensions exist at the micrometer scale, they would modify the spectrum of allowable quantum fluctuations. The measured Casimir force between two plates would show a detectable deviation from theoretical predictions in standard three-dimensional space. Experiments using micro-fabricated silicon chips, where tiny cantilevers act as one plate and a flat surface as the other, are hunting for this signature. They measure the force as the gap closes to mere micrometers, a realm where the ghostly influence of quantum vacuum meets the possible contours of hidden geometry. A positive signal from any of these experiments would be a revolution in a box. It would provide the first direct, earth-bound evidence that our universe has more than three spatial dimensions, solving the hierarchy problem by revealing gravity's apparent weakness as a geometric illusion. But the implications would ripple out to the cosmic scale, reshaping the dark universe narrative. Such a discovery would immediately offer a new mechanism for dark matter interactions. If gravity propagates in extra dimensions, then dark matter particles could interact with each other through new channels in the bulk, channels invisible to us. This could explain why dark matter halos have the specific structures we observe, structures that simple collisionless models struggle to replicate. Furthermore, the very nature of dark energy would be recast. The cosmological constant would be intimately tied to the size and tension of the brane we live on, and the geometry of the bulk it floats within. The accelerating expansion of the universe would be a direct consequence of this higher dimensional architecture, a dynamic outcome rather than a mysterious constant. In one precise measurement of a force at the millimeter scale, we could unlock the geometric origin of the cosmos's greatest mysteries, finding that the keys were hidden not in the distant heavens, but in the quiet spaces between things right here at home. A revolution in physics could be announced by something not seen at all. Within the colossal detectors of the Large Hadron Collider, the most profound discovery might be a sudden absence, a significant amount of energy that simply vanishes from the scene. This is the signature of missing transverse momentum, and in the context of hidden dimensions, it is the primary fingerprint we are searching for. When protons collide at nearly the speed of light, they release a storm of energy that condenses into new particles, all flying outward. Our detectors, like a TLS and CMS, are essentially three-dimensional cameras that capture the trajectories and energies of these particles. The laws of physics demand that the total momentum measured perpendicular to the beam line, the transverse momentum, must sum to zero. If we add up all the visible particles and find a large imbalance, it means something invisible and neutral carried that energy away. In our standard searches, this is the hallmark of dark matter particles. But in the geometric picture, the culprit could be a graviton, the particle of gravity, produced in the collision and immediately escaping off our brane into the higher dimensional bulk. From our three-dimensional perspective, it is as if a portion of the collision's fireball stepped through a doorway we cannot see, leaving behind only a gravitational whisper in the form of missing energy. The more energy that disappears, the stronger the hint that it was carried by a particle capable of leaving our dimensional plane. Beyond this ghostly signature, the collider could witness far more dramatic events. If the fundamental scale of gravity is lowered by large extra dimensions, as the ADD model suggests, then the immense energy density at the collision point could warp spacetime itself into microscopic black holes. These would not be the monstrous entities that swallow stars, but fleeting quantum gravitational objects, smaller than a proton and evaporating in an instant according to Hawking radiation. Their creation would be a thunderclap of higher dimensional physics. Their decay, however, would be a fireworks display. As they evaporate, they would explode into a spherical spray of every conceivable type of standard model particle, electrons, photons, quarks, all erupting in a high multiplicity event with no preferred direction. Detecting such an event would be unmistakable, a violent, democratic burst of energy pointing to a moment where the collider probed not just new particles, but a new regime of gravitational geometry. While no confirmed microscopic black holes have been seen, their predicted signatures remain a powerful target, a test of how spacetime behaves at energies where extra dimensions might become relevant. A third, more subtle pattern could emerge from the debris, the harmonic echoes of the Kaluza-Klein tower. If extra dimensions are compactified, the excited vibrational states of known particles could be produced. Imagine the collider creating a particle that looks and behaves exactly like a heavy version of a photon or a gluon, the carrier of the strong force. This would be a Kaluza-Klein resonance. It would be unstable, decaying almost immediately back into the familiar particles we know. The detector would see a sudden excess of events where, for example, two jets of hadrons or a pair of electrons are produced with a very specific combined mass, a bump on a smooth background. This bump is the resonance, the telltale sign of a new, heavy particle blinking into and out of existence. The profound clue would come if we saw not just one such bump, but a series of them at regularly spaced intervals of mass. That repeating pattern would be the harmonic series, the direct musical scale of the compact dimensions geometry, each resonance a higher note on the string of reality. Finding this pattern would be like discovering the universe's tuning fork, providing a direct measurement of the size and shape of the hidden dimensions themselves. Every collision at the LHC is therefore a multidimensional probe, testing whether our reality is a flat stage or an intricately folded structure, with the answers written in the language of missing energy, explosive decays, and resonant harmonies. While particle colliders probe the hidden geometry of the universe from below, nature provides its own colossal accelerators, scattering cosmic messengers across the void. To test the reality of extra dimensions, we can look upward to the violent hearts of stars and the silent depths of black holes. These astrophysical laboratories operate at energies and densities we could never replicate, and their behavior could carry the subtle signatures of a higher dimensional reality. Consider the final, cataclysmic death of a massive star, a supernova. In its core, a neutron star is born, a city-sized object so dense that a teaspoon of its material would weigh 1 billion tons. This newborn object is unimaginably hot, over 1 billion degrees, and it must cool rapidly. Neutrinos, ghostly particles that barely interact, carry away most of this energy in a great flood. But if extra dimensions exist, they could open a new, invisible escape route. Certain proposed particles linked to the hidden geometry, like the lightest Kaluza-Klein partners or Moduli fields, could be produced in this inferno. If they are produced, they would stream out of the star even more easily than neutrinos, stealing energy directly from the cooling core. This enhanced cooling would cause the supernova's neutrino burst to be shorter and dimmer than our three-dimensional models predict. By carefully studying the neutrino signal from past supernova, like supernova 1987A, astronomers can place tight constraints on this possibility. The fact that the observed neutrinos matched expectations over that 160,000-year journey suggests that any such extra-dimensional energy loss is small, helping us rule out certain sizes and couplings for the hidden geometry. The cosmos itself is performing the experiment, and the light from a dying star tells us about the shape of dimensions we cannot see. The fate of the most extreme objects in the universe could also be rewritten by hidden dimensions. A black hole in Einstein's four-dimensional theory is a perfect trap. Nothing, not even light, can escape from within its event horizon. But Stephen Hawking showed that when quantum effects are considered, black holes are not perfectly black. They slowly evaporate, emitting a faint thermal radiation. The presence of large extra dimensions would dramatically alter this story. A higher dimensional black hole, one whose gravity operates in the full bulk spacetime, would have different properties. Its temperature, and thus its rate of evaporation, depends critically on the number of dimensions. In a universe with large extra dimensions, small black holes would be hotter, evaporating far more quickly and violently than their four-dimensional counterparts. They might even be produced in high-energy cosmic events. Furthermore, the way they decay, the spectrum of particles they emit as they evaporate, would be a direct fingerprint of the dimensionality of spacetime. They would not just emit photons and neutrinos, but potentially a shower of higher-dimensional gravitons that vanish into the bulk, searching for the telltale gamma-ray signatures of evaporating primordial black holes, or for unexpected particle bursts from astrophysical sources, becomes a search for the architecture of reality. A black hole's silent dissolution could be a broadcast in a higher dimensional language, detailing the true scale of the cosmos. Beyond stellar cataclysms, the universe sends us individual messengers of unimaginable power, atomic nuclei hurtling through space at nearly the speed of light. These are ultra-high-energy cosmic rays, and they carry energies millions of times greater than anything achievable in the Large Hadron Collider. Their origin is one of astrophysics' great mysteries, possibly linked to active galactic nuclei or colliding galaxies. But for physicists probing fundamental limits, these particles are more than just bullets from deep space. They are probes of spacetime itself. At such phenomenal energies, the effects of quantum gravity might become apparent. If the fundamental scale of gravity is lowered by large extra dimensions, as the ADD model proposes, then these cosmic rays should interact with the cosmic microwave background, the leftover glow from the Big Bang, in a new way. In our standard four-dimensional world, a proton with energy above a certain threshold will collide with a background photon and produce new particles, losing its energy over long distances. This creates a predicted cutoff in the cosmic ray spectrum, which we seem to observe. But if gravity becomes strong at a much lower energy due to extra dimensions, different processes become possible. The cosmic ray could interact via gravitational effects, perhaps producing a microscopic black hole or a cascade of particles through graviton exchange. This would change the expected shape of the cosmic ray energy spectrum and the types of secondary particles we detect. Observatories like the Pierre Auger Observatory are meticulously measuring the properties of these rare, ultra-high energy events. Any statistically significant deviation from the standard model prediction could be a hint that these cosmic bullets are not just traveling through space, but interacting with its full, hidden geometric structure. They offer a natural experiment on a galactic scale, testing the fabric of reality at energies no human machine will ever reach. In the silent rain of particles from the void, we might find the data that finally maps the unseen dimensions of our universe. Gravitational waves have opened a window into the violent, unseen side of the cosmos. When two black holes spiral inward and merge, they do not send out a flash of light or a burst of particles. They shake the very fabric of spacetime itself, sending ripples across the universe that stretch and compress everything in their path. These ripples are gravitational waves, and our ability to detect them with observatories like LIGO and Virgo has ushered in a new era of astronomy. We are no longer just looking at the universe, we are now listening to its geometry. Every chirp and ring down from a collision is a direct message from the realm of extreme gravity, a pristine signal largely unaltered by its journey through interstellar dust or magnetic fields. This makes these events the perfect laboratory for testing the fundamental nature of gravity and the shape of reality. When scientists analyze the gravitational wave signal from a merger, they match it against precise predictions from Einstein's theory of general relativity. The inspiral, the merger, and the final ring down as the new black hole settles into a quiet sphere all follow a specific mathematical pattern. But what if the signal does not match perfectly? Small deviations, subtle anomalies in the waveform, could be the most important clues we ever find. One tantalizing possibility involves echoes. After the main gravitational wave chirp from a merger, some models suggest that if the object involved is not a classic black hole as predicted by four-dimensional general relativity, but something with a more complex structure influenced by extra dimensions, part of the signal could get temporarily trapped. Imagine dropping a pebble into a well. You hear the initial splash, then a moment later, a faint echo as the sound bounces off the walls. A similar effect could occur if the event horizon of a black hole is modified by higher dimensional physics, creating a gravitational cavity. A faint, repeating echo following the main crash could appear in the data. While such echoes remain speculative and controversial, their potential discovery would be revolutionary, pointing directly to a breakdown of classical black hole physics and a signature of spacetime's hidden architecture. Beyond echoes, the entire propagation of the gravitational wave could be affected. If gravity can leak into extra dimensions, then the waves themselves might lose a tiny amount of energy into the bulk as they travel across cosmic distances. This would be an incredibly subtle effect, like a sound growing very slightly fainter, not just because it is spreading out, but because some of its energy is seeping through the walls of the room. Over millions or billions of light years, this leakage could imprint a specific distortion on the waveform, a deviation from the clean prediction of general relativity. As we collect more and more events from across the universe, we can start to look for these statistical whispers in the data. Each cosmic collision is not just a spectacular event, it is a stress test for spacetime, probing whether the fabric of the universe is a simple three-dimensional sheet or a more complex multidimensional structure. The silent ripples from the darkest places in the cosmos may be carrying the clearest map of all, a direct recording of reality's true geometry. The most ancient light in the universe holds a frozen record of its first moments. This is the cosmic microwave background, a faint afterglow that fills every corner of space, a snapshot of the infant cosmos when it was just 380,000 years old. Its temperature is nearly uniform but not perfectly so. Tiny fluctuations, mere millionths of a degree, form an intricate map of hot and cold spots, a blueprint for all the structure that would later form galaxies and clusters of galaxies. We have mapped this relic radiation with incredible precision using satellites like Planck and WIMP. The overall pattern fits our standard model of cosmology beautifully, but a few stubborn anomalies linger at the very edge of statistical significance. These are subtle quirks in the data, places where the temperature variations are a little too aligned, or a large-scale feature appears unexpectedly cold. While they could be mere statistical flukes, they are also potential cracks in the standard story, hints that the physics of the very early universe was not exactly as we have modeled it. This is where the geometry of hidden dimensions could leave its most primordial signature. To understand how, we must go back to the universe's first fraction of a second, to the theorized period of inflation. In our standard three-dimensional picture, inflation is a brief, hyper-accelerated expansion that smoothed and stretched the cosmos to its remarkable uniformity. It was driven by a hypothetical field, the inflaton. Now consider that early universe within a higher dimensional framework. The inflaton field would not be confined to our three-dimensional brain alone. It would be a higher dimensional entity, its energy and dynamics influenced by the full geometry of the bulk. The process of inflation itself, and any subsequent phase transitions as the universe cooled, would be fundamentally different. The way quantum fluctuations were stretched into the seeds of cosmic structure would carry an imprint of that multidimensional physics. Think of it like the vibrations of a drumhead. The pattern of sound it produces depends entirely on the drum's shape and tension. If our three-dimensional space is a membrane within a bulk, then the quantum fluctuations that became the CMB were vibrations of that brane. The specific way those vibrations were amplified and frozen into the sky would depend on the brane's tension, its coupling to the bulk, and the geometry of the extra dimensions themselves. This could manifest in the CMB map as specific statistical anomalies. For instance, the distribution of the sizes of hot and cold spots might show a subtle preference for certain scales, a harmonic series echoing the size of a compact dimension. Or the way the light is polarized, the direction its electric field vibrates, could carry a pattern that is difficult to generate with simple three-dimensional inflation, but emerges naturally if the inflaton field could tunnel or oscillate into an extra dimension during those first moments. Missions like Planck have scrutinized the CMB's temperature and polarization patterns with microscopic precision, searching for any deviation from Gaussian randomness, any sign of a preferred direction or unusual correlation between different scales. One persistent, though not conclusive, anomaly is an apparent alignment of the largest scale fluctuations, sometimes called the axis of evil. Another is a mysterious cold spot, a large region significantly cooler than the surrounding average. While these could be artifacts of our local universe or statistical noise, they are also the places where theorists look for the fingerprints of new physics. If the early universe experienced a phase transition involving the compactification of extra dimensions, as some string theory models suggest, the release of energy and the formation of topological defects in that process could have left scars on the CMB. These would appear as specific, non-Gaussian patterns in the temperature map, subtle swirls or discontinuities that our standard models cannot easily produce. Searching for these imprints is an exercise in cosmic forensics, sifting through the oldest possible crime scene for evidence of a reality with more dimensions than we see. The CMB is our only direct window into that primordial era, and its faint whispers, if decoded, could tell us that the universe's geometry was written in more than 3 dimensions from the very beginning. But this elegant geometric vision faces a profound and humbling challenge. The mathematics of string theory and extra dimensions does not lead to one unique solution, but to an almost unimaginable multitude of possibilities. This is known as the landscape problem, and it presents a theoretical hurdle that reshapes the entire nature of our search. The equations allow for a staggering number of stable ways for the extra dimensions to be curled up and shaped, each with its own intricate geometry. Estimates suggest this number could be as vast as 10 to the power of 500, a figure so large it dwarfs the number of atoms in the observable universe. Each distinct shape in this cosmic landscape corresponds to a different set of physical laws in our three-dimensional world. The size of the compact dimensions, the way they are twisted and connected, determines the masses of particles, the strengths of forces, and the value of the cosmological constant. In one possible configuration, electrons might be heavy and gravity strong, resulting in a universe where atoms never form. In another, the numbers align just right to produce a cosmos like ours. The problem is one of prediction. With so many possible shapes for the hidden geometry, how can we ever know which one is real? How can a theory that allows for everything predict anything specific about our world? This vast landscape complicates the hunt for dark matter and dark energy immensely. The gravitational leakage explaining dark matter, or the evolving geometry behind dark energy, are not tied to a single, unique model. They could arise from a near infinity of different compactifications. The specific particle that constitutes dark matter in one geometric configuration could be completely different in another. The value of dark energy could be a consequence of one particular brane tension or bulk curvature among countless others. This means we cannot simply calculate from first principles and say, the dark matter particle has this mass or dark energy will behave in that way. The landscape transforms the search from a deductive puzzle into a grand, observational treasure hunt. We must use the data from our universe, the specific numbers we measure, to navigate this immense terrain of possibilities. It forces a more humble, data-driven approach. Instead of asking the theory to tell us exactly what to look for, we must ask our experiments and observations to tell us which path through the landscape we are actually on. Every new piece of data, from the mass of the Higgs boson to the distribution of galaxies, acts as a signpost, ruling out vast swaths of the landscape and guiding us toward the region that matches our reality. The quiet in our dark matter detectors, the precise rate of the universe's acceleration, the subtle anomalies in the cosmic microwave background, these are not just mysteries to be solved. They are the coordinates we are using to map the true geometry of everything. The landscape does not make the quest impossible, it makes it empirical. We are not deriving the universe from pure thought. We are discovering its shape, one measurement at a time, slowly learning which of the 10 to the 500 possible worlds is our home. The sheer number of possibilities within the landscape leads to a serious and valid question, one often raised from outside the field. If the theory allows for so many outcomes, how can it ever be tested? Is the idea of hidden dimensions just elegant mathematics, or is it real science? The bedrock of the scientific method is falsifiability, the principle that an idea must make predictions that can, in principle, be proven wrong by experiment. Critics argue that concepts like string theory and extra dimensions fail this crucial test, residing in a realm of untestable beauty. This is a vital challenge, and it deserves a direct response. The answer lies not in the abstract whole of the theory, but in the specific, concrete models that emerge from it. While the full mathematical landscape may be vast, individual pathways through it generate sharp, unambiguous predictions for our observable universe. We are not searching for evidence of extra dimensions in a vague, general sense. We are hunting for the fingerprints of very specific geometric configurations. Consider the tests we have already outlined. The search for deviations from Newton's law of gravity at sub-millimeter distances is a direct quantitative probe. A tabletop experiment that finds no deviation down to a certain scale actively falsifies all models predicting large extra dimensions larger than that scale. It is a clean, binary test. At the Large Hadron Collider, the signature of microscopic black holes or a sequence of Kaluza-Klein resonances are not vague notions. They are specific event topologies with defined properties. If the LHC reaches certain energy thresholds and sees no such signals, it will rule out whole classes of models that predicted those phenomena. Each null result is not a failure but a successful falsification, narrowing the landscape and guiding theorists toward more promising geometries. In astrophysics, the precise timing of a pulsar network or the detailed waveform of a gravitational wave merger are exquisitely sensitive probes. A deviation from Einstein's predictions in the ring-down of a black hole could point to a higher dimensional object, while a perfect match constrains the possibilities. Even the subtle statistical quirks in the cosmic microwave background are not just curiosities, they are data points. Specific models of brane inflation or early universe phase transitions predict specific, non-Gaussian patterns. Our ever more precise maps of this ancient light are actively testing those predictions, searching for a match that would select one geometric history out of countless others. The complexity of the overarching framework does not invalidate the testability of its children. General relativity is a profound and complex theory, but we did not test it by contemplating the entirety of curved spacetime. We tested it by looking for the bending of starlight during a solar eclipse, a single, clear prediction. In the same way, the hunt for the geometric universe proceeds through these focused, empirical missions. The idea that hidden dimensions might reshape dark matter and dark energy is not untestable speculation. It is a hypothesis that generates a rich menu of experimental targets, from the quiet of a laboratory vacuum chamber to the echoes of colliding black holes. Our task is to follow the data wherever it leads, even if the path points toward a reality with more doors than we ever thought possible. The most elegant solution would not invent two separate mysteries, but reveal one profound source. This is the ultimate promise of the geometric vision, a single origin for the entire dark sector, where both the structure and the fate of the cosmos emerge from the same hidden architecture. The key lies not in particles, but in a field that defines the very shape of reality. In theories with extra dimensions, the size and configuration of those curled-up spaces are not fixed by a cosmic decree. They are dynamic, governed by a field known as a Moduli field. Think of it as the master dial for the universe's compact geometry, a value that determines the radius of every hidden circle and the angle of every unseen twist. In the earliest moments after the cosmos began, this field would have been wildly oscillating, a chaotic pendulum swinging through the landscape of possibilities. As the universe expanded and cooled, this field began to settle, seeking its lowest energy state, the most stable geometric configuration. But its journey toward that final rest was not instantaneous, and the phases of that journey could explain everything we see. In its youth, the Moduli field would have been massive and slow-moving, its oscillations frozen into the fabric of the cosmos as it settled, would have created coherent, wave-like structures across space. These are not waves of water or sound, but waves in the field's value itself, regions where the size of the extra dimensions is slightly different. Where the field's value is higher, the energy density is greater. These overdense regions would have acted as gravitational seeds, pulling in normal matter through their gravity. Crucially, because this field interacts almost exclusively through gravity, these clumps would be invisible, yet they would possess mass and shape the cosmos. They would behave exactly as cold dark matter does, providing the gravitational scaffolding for all the galaxies we see. In this phase, the Moduli field is not a substance, but a dynamic geometry that impersonates a substance perfectly, its frozen ripples forming the cosmic skeleton of dark matter. But the story does not end there. As the universe aged, the field continued its slow evolution. Eventually, its oscillations dampened, and it began to approach its final, stable value. But what if that final state is not a static point, but a gentle, rolling descent? Imagine the field as a ball rolling down a very long, very shallow valley. At first, it rolled quickly, its energy dominating as kinetic motion, which manifested as dark matter. Now it is nearing the valley floor, rolling so slowly that its energy is dominated by its potential, the energy stored in its position on the slope. This potential energy, spread uniformly throughout the vacuum of space, exerts a constant negative pressure. This is the phase we are in now. The same field that once clumped to form dark matter halos now manifests as a smooth, repulsive force accelerating the expansion of the universe. It has transitioned from behaving like cold dark matter to behaving like dark energy. In this unified picture, the two great pillars of the dark sector are not separate entities at all. They are two different costumes worn by the same actor at different acts in the cosmic play. The Moduli field, the director of hidden geometry, plays the role of structure builder in the universe's youth, and then transforms into the agent of cosmic acceleration in its maturity. This solves a profound aesthetic problem in cosmology. We observed two dominant, unexplained components, and instead of proposing two separate, unrelated fixes, this geometric approach offers one elegant narrative. It tells a continuous story where the dark universe evolves naturally from the early, dynamic settling of spacetime's shape to its long, slow relaxation today. The transition from a matter-dominated era to a dark energy-dominated era is not a coincidence or a switch being flipped, but the inevitable consequence of a single field finding its rest. If this is true, then the fate of the cosmos is written in the final value of this field. Will it settle into a true minimum, causing the acceleration to eventually cease, or will it continue its slow roll indefinitely, leading to an eternal, accelerating expansion that empties the cosmic horizon? The answer lies in the precise shape of the geometric landscape, a topography we are only beginning to map. This vision unifies the darkness not by finding a particle, but by listening to the deep, patient rhythm of space itself, changing its tune across the eons. The vast landscape of possible geometries forces us to confront a staggering possibility. If our universe's specific configuration, with its particular dark matter density and tiny dark energy value, is just one point in a space of 10 to the 500 options, then why does it look this way? One controversial answer emerging from this line of thinking is that perhaps there is no deeper why from a fundamental equation. Instead, our physical laws, including the nature of the dark sector, might be environmental. This is the Multiverse Hypothesis, and it radically recontextualizes our entire search. In this view, the string theory landscape is not a menu of mathematical possibilities, but a map of actual, existing universes. Each stable configuration represents a separate, physically real cosmos within a grand, higher-dimensional multiverse. In these other universes, the compactified dimensions are curled differently, leading to wildly different physics. In most of them, the numbers would not allow for atoms, stars, planets, or life. The cosmological constant might be enormous, ripping space apart instantly, or gravity might be so strong that any structure collapses immediately. Our universe, with its curiously balanced forces and its specific dark matter and dark energy properties, is not special because it is the only one, but because it is one of the extremely rare islands in the multiverse where conditions are just right for complex structures and ultimately for observers like us to arise and ask these questions. This principle is often called anthropic reasoning. It suggests we should not be surprised to find ourselves in a universe compatible with our existence, even if such a universe is statistically vanishingly rare in the wider multiverse. From this perspective, dark energy is not a puzzle to be derived from first principles, but a feature we observe because we are here to observe it. Its incredibly small, non-zero value is not predicted by a unique theory, but is simply a parameter that falls within the narrow window allowing for galaxy formation and life. The same logic applies to dark matter. Its abundance and properties might be what they are because that specific type of geometric configuration, perhaps one where Moduli fields freeze into the right clumpy patterns, also happens to produce a universe capable of forging stars and planets. This idea is deeply controversial because it seems to shift the goalposts of science. Instead of a unique, elegant theory explaining why the constants of nature must be exactly what they are, we are left with a cosmic lottery. Our search transforms from seeking a single why to mapping a probability distribution. We are not looking for the one theory that predicts our universe, but for the theory that predicts a multiverse in which a universe like ours, with these specific dark properties, is possible and perhaps even inevitable within some statistical spread. The task becomes to understand the rules of the landscape itself, the mechanisms by which baby universes with different geometries are spawned, and to see if the distribution of possible physical laws within that multiverse naturally includes a non-zero fraction that look like our home. This does not make the questions less meaningful, it makes them different. We are no longer just astronomers and particle physicists, we are cosmic cartographers and statisticians, trying to understand the demographics of reality. The quiet specifics of our dark universe, the precise way galaxies are clustered, and the exact rate of acceleration become the crucial data points. They are the local measurements we use to infer the shape of the entire multiversal landscape, to understand what kind of neighborhood we live in. It suggests that the darkness we cannot see might be the most important clue we have, not just to the geometry of our space, but to the breathtaking scope of all that exists. The search for hidden dimensions, whether it ultimately succeeds or fails, is already reshaping our world. This journey into the deepest questions of reality does more than just probe the cosmos. It spins off technologies and insights that ripple through our entire scientific and technological landscape. Consider the quiet heart of a gravitational-wave observatory like LIGO. To detect a ripple in spacetime smaller than 1/10,000th the width of a proton, scientists had to conquer noise at an almost impossible level. They pioneered techniques in ultra-high vacuum systems, developed seismic isolation platforms that float on layers of pendulums, and perfected lasers of unimaginable stability. These are not just tools for astronomy, they are masterclasses in precision engineering. The same cryogenic systems that cool dark matter detectors to near absolute zero are now informing designs for quantum computers. The advanced data analysis algorithms created to sift a faint gravitational wave signal from a sea of terrestrial noise are being adapted for medical imaging and financial modeling. The pursuit of the universe's hidden geometry forces us to build a quieter, more sensitive world, and those skills transform industries far beyond fundamental physics. On the theoretical front, the mathematics forged to describe extra dimensions has become an unexpected toolkit for understanding our own. The concept of holography, which emerged powerfully from string theory, proposes a breathtaking equivalence that a theory of gravity in a volume of space can be perfectly described by a quantum field theory living on its boundary, like a three-dimensional hologram encoded on a two-dimensional surface. This abstract idea, born from thinking about black holes and higher dimensions, has ignited revolutions in seemingly unrelated fields. In condensed matter physics, researchers now use holographic methods to model the chaotic behavior of exotic materials like strange metals, which defy classical explanation. The mathematical techniques developed to navigate the landscape of string theory have provided powerful new ways to calculate in ordinary quantum field theories, solving problems that were once intractable. Even if the specific vision of large extra dimensions is not realized, the intellectual machinery built to explore it has gifted us with new lenses through which to examine everything from the quark-gluon plasma to quantum entanglement. This is the hidden dividend of curiosity-driven science. We set out to map the geometry of the cosmos, and along the way we invent new ways to see, measure, and calculate. We build machines that listen to the whisper of spacetime and, in doing so, learn to control our environment with unprecedented finesse. We develop mathematics to describe hidden dimensions and find it can crack open mysteries in the materials in our hands. The value of the quest is not contingent on a single, final answer. It is embedded in the path itself, in the technologies spun off from extreme engineering and the conceptual bridges built between distant corners of knowledge. Whether the universe has 10 dimensions or 3, the act of asking the question compels us to become better makers, better thinkers, and better observers of the intricate reality we call home. Proof would not arrive in a single, blinding flash of light. Instead, it would unfold as a slow, meticulous convergence, a story told by 3 different languages of science, each speaking of the same hidden geometry. This timeline of discovery might begin not in the cosmos, but on a quiet laboratory bench. After years of refining their delicate torsion, balances, or Casimir force apparatus, a team of experimentalists publishes a result that sends a tremor through the foundations of physics. They have measured the gravitational force between 2 microscopic masses separated by a mere hundredth of a millimeter, and the force is stronger than Newton's law predicts. The deviation is small, just a few %, but it is statistically undeniable and repeatable. At distances smaller than the width of a human hair, gravity begins to behave differently. This would be the first brick in a new foundation, a direct signal that spacetime has more room than we thought, that gravity is indeed spilling into an extra dimension just beyond our everyday perception. The immediate question from the particle physics community would be sharp and focused. If the extra dimensions are this large, what energy scale does that imply for quantum gravity at the LHC? The second act would play out in the cavernous halls of the Large Hadron Collider. Armed with the new scale suggested by the tabletop result, theorists would refine their predictions. They would tell experimentalists at detectors like a TLS and CMS to look with renewed intensity in specific, narrow energy ranges for 2 possible signatures. The first could be a sudden excess of events with large missing transverse momentum, the telltale sign of gravitons sailing off into the bulk. The second, even more dramatic, might be the appearance of a new, heavy particle that decays into known particles, a Kaluza-Klein resonance. Imagine the announcement, a few years after the gravity deviation, of a new particle discovered at the LHC with a mass of, say, 5 teraelectronvolts. It decays into pairs of photons or electrons with a clean, sharp peak in the data. Crucially, its properties do not match any predicted supersymmetric particle, but its mass and decay patterns align perfectly with the lightest excited state of a photon or a gluon in a specific geometric model, one consistent with the size of the extra dimension just measured on Earth. This would be the second powerful convergence, a particle from the debris of a proton collision that points directly to the same hidden geometry, first hinted at by a gentle force between 2 tiny gold spheres. The final, majestic confirmation would come from the silent ripples in spacetime itself, as gravitational-wave observatories like LIGO, Virgo, and future space-based detectors like LISA accumulate more and more black hole merger events. Astrophysicists would perform a grand statistical analysis. They would compare the observed ring-down signals, the final quivers of the new black holes, against the pristine predictions of 4-dimensional general relativity. In a universe with large extra dimensions, even slightly, the way a black hole vibrates as it settles is different. The frequencies of its ring-down are shifted, and its waves might dampen a tiny bit faster due to energy loss into the bulk. Individually, each event might be consistent with Einstein, but collectively, across dozens or hundreds of mergers, a subtle, persistent statistical anomaly would emerge. The data would show a slight but systematic deviation, a fingerprint that cannot be explained by astrophysical uncertainties or instrument noise. This third pillar, emerging from the most extreme gravitational environments in the universe, would seal the case. It would demonstrate that the same geometric modification affecting tabletop gravity and particle collisions also governs the behavior of the most perfect gravitational objects in nature. This convergence from 3 wildly different frontiers, cosmology, particle physics, and precision measurement, is what true proof would look like. No single experiment could ever be definitive on its own. A tabletop anomaly might have an unforeseen systematic error. A new particle at the LHC could be something else entirely. A slight skew in gravitational wave data might be due to unknown astrophysics. But if all three lines of inquiry point to the same scale, the same geometric parameters, the evidence becomes overwhelming. It would show that the hidden dimensions are not just a mathematical curiosity, but a physical reality that manifests consistently across every realm of inquiry, from the quantum to the cosmic. The discovery would rewrite textbooks not with a shout, but with a chorus, a harmony of data singing in unison about the true, folded shape of our universe. Such a discovery would not merely add a new chapter to physics, it would rewrite the entire book of reality. For centuries, our scientific quest has been built on a foundational assumption that the stage of the universe is the three-dimensional space and one-dimensional time we directly experience. Everything from the orbit of planets to the collision of particles has been a drama played out on this four-dimensional platform. We have hunted for the actors, the particles and forces, believing that if we could just find all the characters, the plot would make sense. Dark matter and dark energy have been the mysterious, unseen actors we have been desperately trying to cast, but confirming hidden dimensions changes the story at its core. It tells us we have been mistaken about the stage itself. The platform is not flat and limited, it is a rich, multidimensional structure, and we are confined to a single, three-dimensional slice of it. The actors we perceive are not missing. They are performing in a theater we have not yet learned to see. The hunt for dark matter transforms from a search for a ghostly substance within our world to a cartographic mission to map the contours of a larger reality. We are not looking for a thing, but for a shape. The gravitational pull attributed to dark matter could be the gentle warping of our brain by a parallel universe or the weight of vibrating extra dimensions. The accelerating expansion driven by dark energy might not be a force at all, but the slow, inevitable relaxation of that hidden geometry over cosmic time. This shifts the nature of explanation itself. Instead of asking what particle causes this gravity, we would ask what curvature in the higher dimensional bulk projects this shadow. The answer is no longer a list of ingredients, but a blueprint of the architecture. It moves science from a chemistry of the cosmos to a cosmology of geometry. Our reality becomes a kind of cosmic illusion, a hologram or a projection of a more complete, higher dimensional truth. The solidity of the world around us, the very three-dimensional nature of our existence, would be revealed as a persistent, profound limitation of our perception. We are like the inhabitants of Plato's cave, mistaking the shadows on the wall for the full substance of reality. The confirmation of extra dimensions would be the moment we turn around and see the fire, the objects, and the higher dimensional world casting those shadows. It forces a humbling yet exhilarating philosophical pivot. We must accept that our most direct, visceral experience of the universe is a partial view, a low-resolution projection of a far more complex and beautiful whole. The deepest mysteries of the cosmos, the darkness that shapes it and drives it apart, would no longer be flaws in our understanding of the local stage, but essential clues to the true, grander geometry of everything. Our quest becomes one of learning to read the universe not just as a collection of objects, but as a single, magnificent, multidimensional shape, whose hidden folds hold the light we have been searching for all along. The current experimental silence is not an end, but a narrowing of the path. So far, the most sensitive searchers have come back empty-handed. The Large Hadron Collider has found no microscopic black holes, no clear signs of Kaluza-Klein resonances, and no definitive missing energy events that cannot be explained by standard processes. Similarly, the exquisitely precise tabletop tests for deviations in Newton's law of gravity have seen nothing unusual down to scales of about 1/100th of a millimeter. These null results are not failures, they are powerful data points. They have ruled out entire families of models, particularly those predicting large extra dimensions accessible at these energies and distances. The landscape of possibilities is being pruned, guiding theorists toward more subtle and intricate geometric configurations that might still hide just beyond our current reach. This quiet phase is a necessary prelude, a moment where the universe asks us to look deeper, to listen more carefully, and to build better tools. The next decade will see a leap in our ability to probe this hidden architecture. On the energy frontier, plans are already underway for a new generation of particle colliders. The Future Circular Collider, or FCC, proposed to be built in a 100-kilometer tunnel beneath Europe, would smash protons together at energies up to 7 times greater than the LHC. This immense jump could finally reach the mass scale of the lightest Kaluza-Klein particles in many models, or produce the telltale graviton emission that has so far remained elusive. Alongside it, the International Linear Collider, or ILC, would use pristine collisions between electrons and positrons to measure with exquisite precision the properties of any new particles discovered, acting as a perfect microscope to distinguish a geometric resonance from other exotic possibilities. Our view of the cosmos will also expand dramatically. In space, the Laser Interferometer Space Antenna, LISA, is scheduled to launch in the mid-2030s. This trio of spacecraft, flying in a triangular formation millions of kilometers apart, will form a gravitational-wave observatory of staggering sensitivity. It will detect the mergers of supermassive black holes from across the universe, and its pristine, low-frequency hearing will be perfect for catching the faint echoes or modified ringdowns that could betray the influence of extra dimensions around these colossal objects. It will listen for the whispers of the bulk in the most violent events imaginable. Closer to home, but looking back to the very beginning, a new generation of telescopes will stare into the cosmic microwave background with unprecedented clarity. The Simons Observatory in Chile and the even more ambitious CMB S4 project will map the temperature and polarization of this ancient light with microscopic detail. They will search for the subtle, non-Gaussian patterns, the statistical anomalies that could be the frozen imprint of a multidimensional inflattened field or a phase transition in the geometry of the early universe. These projects are not separate endeavors, they are a coordinated campaign. The particle colliders probe the high-energy behavior of gravity and the possible echoes of compact dimensions. The gravitational-wave observatories test the large-scale geometry of spacetime around extreme objects. The CMB telescopes examine the primordial seeds of structure, potentially shaped by higher dimensional physics. Together, they form a three-pronged assault on the mystery, a collective effort to answer one profound question: is the darkness we cannot see a substance, or is it the shape of space itself? The next chapter of this story will be written not by a single experiment, but by the convergence of data from across the spectrum of reality. The darkness is not an oversight, it is a direct challenge. For nearly a century, the twin mysteries of dark matter and dark energy have stood as more than just missing pieces in our cosmic inventory. They represent a fundamental crisis in our very description of reality, a clear sign that the map we have been using no longer matches the territory. Our most successful theories, brilliant as they are, stare into the void and see only a question mark. This is not a failure of science, but its greatest opportunity, the moment where we are compelled to question the stage itself, not just the actors upon it. The hypothesis of hidden dimensions, while still speculative, emerges from this crisis not as a wild fantasy, but as a coherent and deeply elegant framework. It dares to ask if the answers we seek are not hidden in the darkness, but in the geometry of the light. In one sweeping vision, it offers potential solutions to puzzles that have long seemed disconnected: the baffling weakness of gravity, the ghostly nature of the dark sector, and the impossibly small value of the cosmological constant. It proposes that these are not three separate problems, but three different shadows cast by a single, unseen structure, the true, multidimensional shape of space. This idea transforms the search from a hunt for unknown particles into a map-making expedition of reality's hidden architecture. The beauty of this approach is that it is not merely a beautiful story, it is a testable one. It makes concrete predictions, from the behavior of gravity at microscopic scales to the echoes in colliding black holes, that our most advanced experiments are actively pursuing. The quiet we hear so far is not a dismissal but a guide, narrowing the path and sharpening our questions. It reminds us that science, at its core, is this profound willingness to question the fabric of everything we think we know. To look at a universe where 95% is hidden and ask, not what is missing from our picture, but what is missing from our perspective. This search, across underground labs, particle colliders, and space telescopes, is a testament to that restless curiosity. As these experiments push into new frontiers over the coming decade, each new result, whether a detection or another profound silence, will bring us closer to an answer. We may discover that our universe is a grand, multidimensional tapestry, or we may find that its geometry is simpler than we dared to dream. Either way, the journey to understand the darkness is reshaping our place in the cosmos, reminding us that the greatest discoveries often begin by learning to see the world not as it appears, but as it truly is.